Okay, this is lecture 21, continued discussion about circuit simulation. Let's go to the review of our previous lecture, lecture 20. So, in the lecture 20, we have introduced SPICE. So, SPICE is the standard name for all kinds of circuit simulators. So it adopts modified nodal analysis. So simply speaking, Kirchhoff's current law is applied to every circuit node. Of course, if we apply certain KCL, then KCL simply means that the sum of branch current should be 0. So directional one, incoming or outgoing. So we have to understand what is this branch current. I1, I2, I3. If we have 3 branches, then it states that sum of I1, I2, and I3 should vanish. Then the natural question is, what is the form of I1 and what is the form of I2 and I3? It really depends on the nature of the circuit element attached to this branch. So we need additional equations for branch current. So in this case, if we have a resistor or inductor or capacitor, then that will determine the behavior of our branch current. RLC is they are quite simple circuits. However, we are more or less interested with this MOSFET. So how can we specify a MOSFET in this SPICE? Command file. So starting from M, yes, it is recognized as an MOSFET, and here we have drain node, gate node, source node, body node. After that, the type is specified, for example, NMOS or PMOS, and width and length. Of course, you know there are so many other parameters which can be specified in this case. So, in order to specify the MOSFET, we need something. And simulation method, there has been .dc, .trans, this is a transient simulation, and this is DC simulation. Of course, not only these two, we have additional simulation method available in the SPICE program. Okay, so today's topic is very specialized, so we will continue to discuss about device models used in the SPICE. Okay, so simply speaking, we are considering what is the model for our transistor MOSFET. Here we have so-called level 1 model. So level means that SPICE allows many different levels of our MOSFET model. So we have tons of different levels, and some of them are widely used and some of them are seldom used. So I want to say that this level 1 is the simplest one we can use in the SPICE. So is it practically important? Actually not. It is just shown here only for educational purpose. So in the reality, we do not use this level 1 model. Its basic current model is quite simple. So for example, when we have gate voltage lower than threshold voltage, then current is 0. Yes, we have seen it before. And how about the linear region? Of course, gate voltage is now higher than this threshold voltage, but we have still low drain bias. In this case, we have this form. So what is this? Un Cox is this Kp parameter and W over L, and here we have a certain factor. So maybe you are quite much familiar with this factor, and even in the saturation region, then you can find the same one. So here you have a quadratic dependence on the gate overdrive voltage, and here we have a factor of 1 over 2. Okay, so you know it. So compared with our previous IV characteristics already discussed in this course, the only difference is this one here. We have additional drain bias dependence. So for example, in this case, saturation current usually does not depend on VDS. So for example, if we take the partial derivative of our saturation current with respect to VDS, then in our previous model it is 0. So let me just draw our output characteristics. For example, ID, and here we have VDS, and we are now talking about the saturation mode. So let's say that this is a knee point, and now we have saturation. So this is a saturation current. So if we slightly change our drain voltage from here to there, then what is expected increase over our drain current? Actually, it is 0. So from the viewpoint of our drain terminal, actually we can expect infinitely large output impedance or output resistance. However, in reality, it is not so. So we have a certain finite slope shown in this, even in this saturation region. So this part is described with this additional factor, like 1 plus 1 was there. However, additionally we introduced lambda times VDS. So our IV curve just looks like this. If we have large lambda value, for example, then we will have steeper behavior, and if we have lambda quite close to 0, then we will just convert or come back to our previous perfectly long channel ideal characteristics. So this lambda just to describe the output resistance of our transistor. So now let's go to other part. Of course, here we have to specify the threshold voltage. Then who determines the threshold voltage? Yes, we can define threshold voltage at 0 substrate bias. So this is the parameter we can specify. And also the so-called surface potential can be specified, and this gamma factor is also another parameter. So following this expression, if we apply 0 source to body voltage, then of course this part will not contribute at all. So our threshold voltage will be just VTO. However, if we have a certain positive voltage, then the difference between these two numbers will not be 0. That will be a positive number, and depending on this gamma factor, we will have increased threshold voltage. So for applying positive source to body voltage, we can expect the threshold voltage is increasing, and that is related with the PN junction between our source and substrate. So you can easily understand this one. Actually, you have already seen this expression in the previous lecture with a slightly different notation. And now let's go to the oxide thickness. Yes, in the case of oxide thickness, it is easily calculated from T ox. So you can, for example, say that C ox can be written by W effective multiplied by L effective, also calculated by permittivity of our silicon dioxide divided by this T ox parameter. Of course, this is quite crude or approximation, but anyway, it is working, so we will use. Actually, it is being used in the level 1 model. Of course, for more advanced models, we need better fit for oxide thickness. Okay. So now let's go to this example. I took it from our textbook example, figure 8.12, and this one shows a sample of level 1 model. So that model specifies the specific name model, I mean the MMOS. So when you say that MMOS, actually it is NMOS. So can you understand? So this is already given, preserved, reserved word, and this is your symbol. So you can say that instead of MMOS, you can give any nickname, because you know in this circuit you can have many different N MOSFETs. So therefore you have to specify many of them. And yes, please have a look at these ones. For example, level. Level 1 means that we will use quite a simple expression studied up to now. And Tox 40 e to the minus 10. So that is corresponding to 40 Armstrong. Yes. And Kp is that one. So we have already covered this Kp parameter. Yes, mu and Cox parameter. And lambda, yes, here we have lambda, and zero biased threshold voltage and surface potential and gamma. So you can understand with these three parameters we can specify the change of threshold voltage with respect to the source to body bias, and other ones are all related with such kind of junction capacitances. So we will not cover this one in this lecture. Yes, so if we go to the DCIV characteristics, you can see it in this way. I intentionally took the ratio of W to length, width to length ratio as 2, the minimum sized one, and drain current as a function of drain voltage is shown here. So compared with previous one, we can observe that there is a finite output resistance originated from our lambda value. So if we have, once again, this is corresponding to our lambda. So if we have a higher lambda value, then we will have steeper increase, and if we have a 0 lambda, we will have just a horizontal line. So this is level 1. This is level 1 model. So level 1 was the simplest one. However, actually it is not that much used, at least in my time. So I remember that when I first started study in this course. Still, the level 3 was also being used. So level 3 is based on empirical equations. So let's make a comparison between level 1 and level 3. Cutoff region, yes, we have still zero current. And own region, oh, what is own region? It is unified in terms of this own region, linear and saturation. They are they are combined in this form. How can we have combined expression? The secret is hidden here as VDE. So VDE is nothing but the smaller one between VDS and VDS set. So what is then VD set? And this is gate overdrive voltage. Okay, VGS minus VT. So if VDS is exceeding this VD set, and actually VDE becomes just VD set, so we can recover our previous notation or expression for saturation current. For example, let's say that this is VD set and VD set. Then what happens now? If we have FV parameter equal to 0, then all of this one becomes just half VD set, this one, and multiplied by VD set once again, so we can recover our previous expression for saturation current. However, if it is so, there is no difference between our model level 3 and level 1. The point is, here we introduce certain expression for f sub b. Yes, here we have something, and this something contains many one. I mean that here we have Fn and Fs, and Fn is considering the narrow width effect. So this is not just a simple parameter. When you open the SPICE manual, then you can find a complicated expression for F sub n. So if we have a narrow width, then we can expect that threshold voltage and other quantities are affected. That is here considered as F sub n. Question is, how can we justify the form of f sub n? The answer is, this model is purely empirical. So they just propose equations or expressions to match the experimental data. So there is no guarantee that their expressions should be valid at every technology node. Actually, previously, Model 3 was regarded as a quite good compromise between accuracy and efficiency. However, it eventually failed to predict good enough result for our modern transistors. So it is not being used anymore. So please just treat it as all the time model. And here we have another parameters like f sub s, and this one just to describe short channel effect. So if we have a short channel, then many effects can also occur here, and this kind of things are just considered here. So you can see that actually this is related with gamma, and this gamma is, where did you use this gamma? So gamma was used to consider this change of threshold voltage with respect to terminal. So this gamma is also used in this part. So it's not that clear why we have to have this kind of thing, but this is really empirical and it worked. So yes, so although I'm not showing their expressions, when you open the manual, you can find that they are quite a complicated function of many different parameters. So they are hidden for simplicity in this slide. But you know that. So already compared with this model or level 1, level 3 contains a lot more parameters, and we have to understand, although here we are just writing in this way, L effective and W effective. In general, this is not the drone length, and also L effective is not the drone length. So they can be different, and depending on MOSFET model, they have also complicated expressions for effective width and effective length. So now this one becomes a little bit going to the art, not just disciplined study, but it becomes a kind of an art. And now we are now going to the BSIM model, our central topic today. Because level 1 and level 3 were used, however, they are too simple to fit everything complicated in this device model or VLSI device. So therefore, actually the standard model of MOS model used in the SPICE is simply BSIM. So this is Berkeley short channel IGBT. What is IGBT? So this is isolated gate FET. So this is a nickname of MOSFET. However, it is seldom used in these days. So MOSFET is just universally accepted name for MOSFET. But anyway, this is the standard model BSIM. I have to say that of course there are other models like for example in Japan, Hiroshima University, they have HiSIM. So also European companies has their own model like PSP. P is a European company named Philips. So also there are other. So for example EKV model from Switzerland, and there are many other models. Yes, they have their own advantages and disadvantages. However, from the viewpoint of impact on the, how can you say, impact on the industry, the BSIM is really outstanding. This can be regarded as a standard model. And when you visit the BSIM group's web page, then it is written like there are now currently 5 sorry about that, maybe typo, 5 models in the BSIM family. So this is I think that this is kind of a historic development. BSIM 4 is quite old one for bulk MOSFET. So bulk MOSFET means that nowadays MOSFET is no longer a planar MOSFET, but this BSIM4 was targeted to the bulk MOSFET, it is shown here. And there were also older models like version 1, 2, 3. So I remember that when I just entered into this field, actually there was the BSIM 3. So BSIM 3 was the version of standard choice. After that, they introduced BSIM 4 and other models. You can see that, wow, we have many things. BSIM 4, BSIM bulk. This is also another bulk MOSFET model. And in between there was many models like BSIM 5 and 6, but their name have been changed. And you know that instead of this bulk one, we have a different flavor mm, matched to the SOI device. SOI means that instead of bulk substrate, we intentionally introduce certain thick oxide layer intentionally. After that, we grow a very thin silicon layer. And on top of this silicon layer, we build our transistors. So everything like this source and drain. And yes, here we have a gate. This kind of device is called as SOI because silicon on insulator. So uh, main advantages of this kind of device is now we don't have any substrate, and substrate does not play any leakage source. And also we can increase the subthreshold slope because we have no bulk capacitance. Well, anyway, this is a special flavor for our SOI device. And here we have IMG. This is independent multi-gate devices. So, but I wanted to say that what is the currently the being used in many cases in the logic simulation. That is certainly I wanted to say that PSIM CMG. So here C means that common multigate. Why we have common and independent? Uh, Previously we had so many different shape of transistors. For example, let's say that one thing that was quite popular was double gate. Double gate means that here we have, sorry about that. For example, double gate means that here we have a silicon and we can have a top oxide and here we can have a bottom oxide. So top oxide and bottom oxide, and they are connected to the top gate and bottom gate. In this case, we can apply a certain gate voltage and a different gate voltage to bottom gate simultaneously. So they can be controlled independently. So this is top and this is bottom. So they can be applied independently. That's the reason why they developed PSIM IMG. However, nowadays, what happens? So nowadays, the shape of a transistor, oh sorry about that, now it is stopped, so let's wait for a while. Okay. Now the shape of our transistor just looks like this. Instead of this independent gate, so now our transistor just looks like this. This is silicon and gate is just covering the three sides of our silicon. So this kind of device is called as FinFET. And in this case, can you apply different bias voltage to this side and that side? Actually not, because it is just one piece of a single metal. So when you apply 0.7 volt to this side, then it is just same for the opposite side. So they are just common. Also, Another shape of our transistor nowadays is, although this is being under mass produced only by Samsung, however, it is expected that there will be other components. So silicon, in this case, now metal is covering the four different faces of this silicon. Of course, between them we have insulators. So in this case, this is called as nano sheet transistor because this silicon is really nanometer size, like its thickness is just around 5 nanometer and its width is kinds of several 10 nanometer size. So this is very thin and narrow line, so nano sheet, and sometimes it is called as GAA transistor. This nanosheet is the name, the nanosheet was originated from the shape of silicon, and the name gate all around is originated from the fact that gate is surrounding the silicon all around. So it is a little bit different one. So for example, we can consider a gate all around the transistor, but which is not a nanosheet. For example, if we make the completely circular silicon, then it is covered by gate, then certainly it can be called as a gate all around the transistor, but this is not nanosheet, but this is nano, sometimes called as nano wire, because they have just a wire shape, not a sheet shape. But difference or distinction between this nano wire and nano sheet becomes sometimes difficult, but anyway, so you understand the naming convention for these devices. So in this case, you can understand gate is no longer independently applied to the transistor. There is only one single gate, and this single bias voltage is applied to everywhere to our silicon channel. So for those cases, actually PSIM CMG is conventional choice for MOSFET model. So do you have any question? If you have a question, then please let me know. Then I will try to answer your question as much as possible. And this vision group is led by Professor Chen Min-Hu, and he is also famous about the inventor of FinFET technology. So he plays quite much. So he invented FinFET, and he is a father of a BSIM model, and he was a CTO of TSMC. Yes, and he is still active. So in the last IDM I met him. Okay, then let's go to some features beyond our previous models like level 1 or level 3. Of course, this is taken from our textbook. So our textbook is a little bit outdated. So we have much more features not summarized in this one. But anyway, it is important to understand important effects we have in the more advanced models, like IV characteristics. One of the serious problems of these models is this one. Whenever your gate voltage is lower than threshold voltage, then drain voltage is just 0, exactly 0. It means that in sometimes you cannot determine the bias voltage exactly, because small voltage differences should be allowed to accurately determine the voltage. However, it is not possible. But BC model, so subthreshold, linear, and saturation, they all have non-zero drain current, and they are continuous and differentiable. So it's not like a continuous means that, for example, let's say, think about this one, ID and VGS. If we have a piecewise linear curve, then is it continuous? Yes, it is continuous. Is it differentiable? Actually, not, although here and there they are differentiable. However, at this knee point, we cannot define the first derivative. However, this model avoid those kind of things. Also, yes, threshold voltage can be a function of length and width, and these conditions or this effect is considered. And another thing is also threshold voltage can be a function of substrate voltage and drain voltage. So this is Dibble. So have you heard about Dibble? So I remember that we have covered the effect called as Dibble. When we have higher and higher drain voltage, actually our transistor conduct more. So in terms of this ID versus VGS, actually we can try two different things, like VDS is equal to or quite close to VDS and VDS equal to VDD. Ideally, we wanted to have really ideal or well-matched line for this subthreshold region. However, due to the Debye effect, when we apply drain voltage which is quite high, then there is a tendency of early turn on. Okay, so you can see that subthreshold current is increased quite a lot. That is given as Dibble. So this effect can be also modeled in the BC model. And another one is velocity saturation, mobility degradation, and other short-channel effect. Maybe you remember this kind of effect. And gate capacitance models. So previously we just consider Cox as simply dependent on 1 over Tox, but it can have many other layout dependent effects that can be considered here, and other ones diffusion capacitance and resistance. Yes, we must consider to full working device model and gate leakage model. So also you remember that we have already covered this gate leakage problem, because when you reduce the thickness of our purely silicon dioxide layer, then gate leakage was increased rapidly. So we introduce a high K material. So now that is much compressed or much suppressed, but still we have to consider gate leakage model, not to underestimate the importance of gate leakage model. So simply speaking, what is the current situation of 2023? So simply speaking, we are using the BSIM CMG. That's it. Okay. And I wanted to show you one especially important or especially interesting uh, topic to you. Like this field is really interesting, uh, personally to me. So yes, so this is a paper by Dr. Song. So in 2009, okay, that was the the age of so many different transistors. Nowadays, there is only one type of transistor, FinFET, and another one, the new one, is nanosheet. That is just well established. But however, previously, more than 14 years ago, there was some active debate on which one will be the future transistor. So now we can understand double gate, surrounding gate. This is called as a nano wire MOSFET, and this is a quadruple gate. Means that this is also gate all around, but its shape is a square. And you can see there was a triple. What is the difference between this one? This one just covers four faces, and this one has only three faces covered. And this is a pi gate and omega gate, whatever. Just name a few of them. So also, what happens to MOSFET models? Since the suggested shape of MOSFETs are so various, so the compact model developers should develop individual models for shape A, shape B, shape C, D, E, F, blah blah blah. So I remember that actually my former boss always complained about so many compact models for slightly modified cross-section shape. So that was the situation. And please have a look at this left figure. When you have a look at the left figure, can you match the shape of this silicon layer to any of them? So here you have a relatively dark region. This is the silicon region. And what is its shape? Is it really a rectangle? Actually not. It has something like a ball used in rugby game. Or anyway, it's like an elliptical shape. So, but not perfectly elliptical. So in this central part, it is flat. And slight difference of this silicon, even in the same device. This is just taken from one shot. This is TM image, and here at the same time we fabricated three different channels of silicon. This is inside the same device, but can you recognize that they have different shape? This one has wider. Even in one batch, it is difficult to really identical shape. So then what will you do is, if you have a small difference of the shape, so will you introduce a new model for that transistor? It is almost impossible. However, that was the situation. So one attempt to solve this problem is just shown in 2016. Oh, here we have silicon layer like a dark yellow line, and from the TM image they have found that okay, we can just treat our silicon channel as a rectangle with rounded corner. That is their observation. if we increase the roundness of this shape, for example, if we have extremely round one, then we can have this kind of behavior. And if we reduce the smoothness or roundness of this corner, then we can recover this perfectly rectangular shape. So now also if we reduce this part, this rectangle part still, if we reduce this part, then eventually we can go to cylindrical, because this one doesn't have any intermediate rectangle, then it becomes perfectly circular. And if we increase the width of this rectangle part infinitely, then it becomes double gate. And in between we have a nanosheet, nanowire, anything. So with this kind of observation, they just divide our device into 3 pieces, and this part are modeled differently, and this inner part is modeled differently. Sounds great. However, it will introduce many different also geometric parameters for model this one. So are you happy with this one? So what is actually used in this BC model, the standard model? So, for example, the real FinFET just looks like this. Can you find any kind of resemblance of this one and this nano sheet device? Actually not. So it means that you have to develop FinFET model, and your FinFET model cannot be applied to your nanosheet model. Then you have to develop another one. However, fortunately, there are so many clever guys in this field, so they have found that instead of that, we can find a unified model. I mean that even though we have this quite much complicated shape, but they have observed that, okay, what we need are just two parameters. One parameter, period. Another parameter is area. It is their observation. So can you understand? For example, what is area in this case? I will just shade that area part. Area means that just area of our silicon region. Yes, that's it. Then how about the perimeter? Perimeter means that the length of our interface, silicon dioxide interface. Yes, if you have these two parameters, then the result is really interesting. So they just took these two parameters and they try to compare their compound modeling result with more accurate result, and it is showing a really good argument. But you know that the same model is applied to this FinFET, and the same model is applied to this triangle shape transistor. The channel has the triangular shape. So if we adopt the traditional approach, then we have to develop another compound model for triangular shape, and we must say that this base and this height, depending on the aspect ratio, everything will be changed. However, without just such kind of a complication, they have found that actually once we understand the perimeter and area of this silicon channel, or in this case the indium gallium arsenide channel, then it can be used to predict the transistor's behavior accurately. That is implemented in this BSIM CMG model. Okay. However, I have found that actually there is no derivation. So what they did, what the authors, the original authors of this idea did when he was in Korea, so was like just observing two extreme cases. One extreme case is double gate. Another extreme case is just nano wire, cylindrical nanowire. I mean that not like this, but this one. So the author of this idea just took two extreme, one extreme and another extreme. Since they are geometrically easy to solve, in these two cases we can get analytic expression and another analytic expression. So he just observed that these two opposite extreme expressions share the same form. From those observations, since these two extremes share the same form, maybe anything in between will share once again the same form. That is his suggestion. And just to show that, okay, any arbitrary shape of a transistor cross-section can be well predicted by my model. So it is working. So it was his contribution and suggestion, and he is now in Apple. And now, so there was no derivation, but nowadays in last year it was proved that it can be rigorously derived, and this is the expression for our inversion charge density. This is the number of our electron charge, so it can be modeled as this form rigorously. And you know, this here you have a P. This P is once again our perimeter. And where do we have area? Here we have area, A star, and this A star is corresponding to area. Simply speaking, for any kinds of complicated cross sections, taking the perimeter and area, then you will get more or less close relation for your inversion charge density. Of course, this is not the end of our story, because you know here we have additional parameters like alpha and beta, so we must consider some certain model for these quantities. But anyway, it is much better than individually modeling every possible cross sections. It is much better. Yes, so, and the final topic I wanted to discuss in today's lecture is so-called neural network model. Currently, BSIM CMG is widely adopted and everybody is using this one. And this graph is taken from Chinese company's presentation in 2 years ago. And x-axis is the version of BSIM model, and y-axis is number of internal parameters we have to specify. So can you recognize the number? The number was around 750, and it is increasing, and now including the gate all around mode, it is also jumping, and now we have more than 1500 parameters for specifying a technology. So previously you had what? You had a TOX, phi, VT0, something like that, KP. But now you must specify 1500 parameters to specify a technology. So number of model parameters is ever increasing. It never decrease and ever increasing. So if you go to a certain company which is fabricating certain transistors, then it has its own workforce for making the compact model. I mean that they do not develop their own BC model. Instead of that, BC model provide 1500 model parameters, and what they do is just to try to match their experimental IV data and compact models predicted IV data perfectly. How? They just adjust these parameters automatically or manually to fit experiment and their prediction. Of course, there are many advertisements or many software says that I can fit these parameters automatically, but in reality it is really time consuming and takes long time. So depending on the report, it takes several months even. So if you have something new transistor, if you wanted to fit the entire new technology, then it takes several months. So can you wait for several months to get a model already when you have the transistor? That is really a big problem. So if you change something, let's say that, okay, previously you had a certain well-established technology, but something happens, so your fab guy just slightly change their technology options, and unfortunately the IB characteristics is quite much affected by this small change in the technology. Then what they do is internally the compact model group inside the fab foundry service should perform a lot of readjustment of these parameters. So it will be quite painful and not that much reliable. So upfront. So nowadays there is a certain attempt to introduce a neural network model. As an alternative way, neural compact models are being investigated. It means that anyhow we have more or less, for example, 1000 parameters. And what we wanted to calculate is just drain current, or not only drain current, source current and substrate current and gate current. No, and what else? We wanted to understand the charges. So what is the drain charge, gate charge, something like that, in order to working with capacitance. So it can be just considered as supervised learning problem. We have so many input parameters. Which one is important? I don't know. And we have so many experimental data. So they can be used this validation. We just insert our parameters, length, width, thickness, or bias conditions, and this neural network will give you certain numbers. Of course, that will be quite awful at a first glance, and it is just trained with experimental data for your MOSFET. If you have a sufficiently large number of experimental data, then you can, well, train this neural network. After this training is over, then what happens? Now you don't have to actually calculate a long lines. So once you insert your numbers, then it will just immediately give you certain IV characteristics. So this sounds quite attractive. It is, if you understand the situation, then it will sound more interesting, because inside this BSIM model, actually every time the BSIM is solving this equation. But this is not the only equation it should solve. It should solve hundreds expressions in order to simply calculate your drain current. So inside it, although we have just a single 4-terminal device, but inside in this BSIM model, actually tons of calculations are internally done. So compared with this heavy computation, actually, although we have to spend a certain amount of computation burden to effort to training stage, but once it is trained well, then this inference, just the calculation of current or charge, becomes quite much more efficient than BC model. So this is regarded as one of the future direction for compact modeling. But I'm not quite sure it is suffered from also certain disadvantages. But anyway, this is the future direction of currently for compact model, guys. Okay, I think that's it for today's lecture for especially MOSFET device models, and I have made a very emphasis on the BSIM CMG model, the model we are currently using. And everybody complain about the slow speed of BSIM CMG model. Although that is really well written, but still, the speed of this model really determines the speed of your SPICE simulation. If you have a better model, then your circuit design can be accelerated significantly. For example, if your model is twice more faster than BSIM CMG, then your simulation time will be just shortened by a factor of 2. So they are always hungry for efficient compact model, and this is quite an important research field. Yes, but unfortunately there are not so many research groups devoted to this one, because BSIM is the real standard, and BSIM group and nowadays Indian group, so IIT, so there is a research group whose professor graduated from this Berkeley group, so they continue to develop BSIM model. Okay. So, do you have any questions? So, I think that today's lecture is a little bit different from our previous lecture contents, but I think that will be quite new to most of you, because this compact model is really an important topic, but not that much introduced to undergraduate or graduate student, because to many of them, it is just there. So, some experts provide it to us. So, okay, do you have any question? No? Then I wanted to wrap up today's lecture, and now we will move to the combinational circuit design. So next chapter. Thank you for your attention.